In this video, we introduce Sungkhan Chang's solution of problem A4, of 2014 Putnam competition. Suppose x is a random variable that takes on only non-negative integer values. The expected values of x, x squared, and x cubed, are 1, 2, and 5. Determine the smallest possible value of the probability of the event x being 0. Let us review a few things about probability. Let pk denote the probability of the event x being k. Since x takes non-negative integers, we only consider 0, 1, 2, and so on, for the values of x. The events x being 0 and x being 1 are disjoint events, in other words, they cannot happen at the same time. This principle remains the same for all other distinct pairs of values. Thus the sum of all pk must add up to 1. The expected values can be interpreted as average values. For example, if we throw a dice 100 times, collecting and summing up the face values, what could be the value of the total sum divided by 100? The expected value can be formulated as a sum of face value times the probability of getting that face value. If a rule of the game is to collect the pth power of the face value, then we will be multiplying the pth power to the probability, as shown in the formula. It seems, these conditions are giving us a system of linear equations on infinitely many variables pk. This first equation came from the fact that the probabilities must add up to 1. This 1 came from the expected value of x. This 1, from the expected value of x squared. This 1, from the expected value of x cubed. The problem is about the probability p0, and by using Gauss's elimination, we can isolate p0. Since we have 4 equations, I need to play with 4 variables. So I moved the infinite sums beginning with index 4, to the other side, and focused on the probabilities p0, p1, p2, and p3. For the equations representing the expected values, the first terms are all 0. Now use p1, in the second row to eliminate p1s in the third and fourth rows. Namely, subtract the second row from the third and the fourth. The coefficients of p2 in the third and fourth rows are 2 and 6. The coefficients of p3 in the third and fourth rows are 6 and 24. Also notice what happened to the right-hand sides of the equations. The sum of k times pk are being subtracted from the rows. Now use 2 times p2 in the third row, to eliminate 6 times p2 in the bottom row. We subtract 3 times the third row from the bottom. The coefficient of p3 at the bottom row becomes 6. Let's look at the right-hand sides. The constant part of the bottom row becomes 1. Inside the summation, we have k cubed, minus 3 times k squared, plus 2 times k. Now we can write p3, without using p0, p1, or p2. And from there, we will backtrack to p0, as in solving a system of equations, given by an echelon form. Here is p3. Substitute it to the third equation, and solve for p2. It is simple algebra, so we shall just state the result. Here is P2. Substitute these P2 and P3 in the second equation. Finally, all P1, P2, and P3 are substituted in the first equation. Here we have a formula for P0. We want to examine the cubic polynomial in K, in the summation. If the part is non-negative, the summation can be no less than 0. Then it will allow us to conclude about the original problem. The derivative of that polynomial is simplified to 3 times x minus 2 squared minus 1. Since k are greater than or equal to 4, the derivative values are positive for such k values. Thus the polynomial tk is increasing. Notice that t of 4 is 12. In other words, the polynomial part is always greater than or equal to 12. Since the probabilities pk can be 0, the summation part is at least guaranteed to be non-negative. Thus p0 is greater than equal to 1/3. The question is, can p0 be actually 1/3? Presenting an example will be sufficient for this question. When p0 is 1/3, p1, 1/2, p2, 0, p3, 1/6, and all other pk are 0, all 4 linear conditions are satisfied. So it is possible. This concludes the proof of the claim, that 1/3 is the smallest probability p0 can be. Thanks for watching.